Hi, welcome back. This is Mark Weitzman. Welcome back to my channel, Theoretical Physics with Mark Weitzman. I'd like to do 3 short lectures on Lecture 4 of Schensted's Short Course, which I skipped over. It's Lecture 4 in the short course, and I highly recommend you read that. She does a very good presentation. I will summarize her presentation in 3 short videos. So we're going to do this is group theory in physics. Schensted Short Course. This will be video 4A, and it will cover lecture Lecture 4, Applications to Quantum Mechanics. So video 4A will cover selection rules. 4B will cover perturbation theory. And 4C will preview continuous groups. Now, in the first lecture of the short course, set out some goals. And we had the basically we'd like to understand how the theory of matrix representations allows us to classify the symmetry types of functions and our second goal was to show that two functions of different symmetry type, sometimes we call them special or basic symmetry, are orthogonal. And 3, any function to which a group of operators may be applied may be expanded in terms of the special symmetry functions. Now we've sort of really accomplished all of these things in the previous 3 lectures. We just called them by different names. For instance, one is just basically irreducible representations. 2 is basically just the orthogonality theorem, which we proved in lecture 3. And then 3 is just the expansion theorem, which we'll show by words is true, but we've sort of established this also. So, and these have applications. When you study quantum mechanics, you'll see things like Clash-Gordon series, Wigner, Eckart theorem, etc. So, with respect to 1, functions belonging to an irreducible rep of the group. Remember, we always start with some kind of symmetry group. Are our basic symmetry types. And if you review what we've covered, for instance, if you take the group of 2 elements, call it the parity group, call it whatever you want to call it, we established that there's 2 representations for the parity group, and basically these lead representations are just the even and odd functions. When you get to more complicated groups, like the dihedral group or the permutation group on 3 elements, then you get to more complicated symmetry types, and you'll get, not only will you get more irreducible representations, but you'll also get higher dimensional irreducible representation, 2-dimensional representations. And these require, because we have non-abelian groups, these require a little bit more sophistication in handling, but we've done that. So the symmetry types are always just represented by the irreducible representations of the group. Now, with respect to 2, we want to we know, and we've sort of shown it, functions belonging to different irreducible representations are in fact orthogonal. So this is our orthogonality theorem, and they're orthogonal with respect to the usual unitary scalar products that we encounter in quantum mechanics. Now these are of the form f comma g is equal to like sum, integral. How many integrals and how many sums depends. Of f star, that's the complex conjugate of f, g, times rho. I'll define rho in a second. dx1, dx2, dot, dot, dot. So the sums are over the discrete variables. Usually spin would be the main example. The integrals are over the continuous variables. Such as position or momentum. And they correspond to these variables, dx1, dx2. Now rho, this is the measure. The measure usually arises from using non-Cartesian coordinates. So, if we're using spherical coordinates, we might have r squared sine theta, dr, d theta, d phi. And if we're using, like, let's say spherical, using polar, we might have r, dr, d theta, so on. So that's where that usually comes in. As we'll see when we discuss continuous groups in more detail, not in the short course, but in the long course, the fact that we can get measures which leads to invariant scalar products is of course interesting. We'll discuss that. So I also want to define, I probably defined it before, but I'll do it again, unitary operator. So an operator A is unitary if for all vectors or functions, whatever you're working with, AF comma AG is equal to F comma G. So it just preserves the scalar product. Okay. So the orthogonality theorem just says that if we have functions belonging to the Knuth irreducible representation and the Knuth prime irreducible representation, and this is the same, this is going to be del nu prime, del alpha prime times v. So F here is a member of the invariant space of the Knuth irreducible representation. G nu prime irreducible representation, and nu is independent of alpha, and finally nu equals nu prime means, this is an important point, I used to forget this point, the reps are identical, not just equivalent. So you could take two irreducible reps with different basis elements, they're equivalent. So You might think nu and nu prime are the same, so we'll get this formula, but it won't work because they're using different basis elements, so we won't always get delta, the rows won't always be orthogonal, and we won't always get this V that's independent of the rows. We have to use identical reps. Okay. So I won't go through the whole proof, but the proof uses, the following two equations. One of which we've seen before. The new one is this one. We write F nu alpha G nu prime alpha prime is equal to 1 over n, the sum from j equal 1 to n of aj F nu alpha, comma, aj G nu prime alpha prime. Now, where does this come from? Well, remember this, because our group is unitary, this scalar product here is just equal to F nu alpha, comma, G nu prime alpha prime. It's independent of J, independent of the group element. So we're just summing this from j equal 1 to n, so we get n times, we divide by n, we get the same thing. So this is the main equation that's used in the proof. And then we use something we've seen before many times, the transformation properties of the special symmetry functions under their respective irreducible reps. So we have this equation, which we've seen many times, the group operator operating on F nu alpha, the sum from beta equal 1 to lambda nu. Remember, lambda nu is the dimension of the space of the nth irreducible representation, and this is the matrix representation, the nth one, corresponding to the group element AJ. You have beta alpha F nu beta, and we use a similar for G, and we use that, and I set 2, I'm going to make it 3. And then we use the orthogonality relations, theorem 3.10, from lecture 3 of the short course. And this is sum from j equal 1 to n. Remember, n is the number, the order of our symmetry group. Gamma I, aj, star, complex conjugate, mu nu, gamma k aj u prime nu prime is equal to n over lambda I del I k del mu mu prime del nu prime. So we use these three equations, and I'll write down. We also use the properties of scalar products. You should be fairly familiar with this one, assuming you've taken a linear algebra course or a quantum mechanics course. It's anti-linear. This alpha star is what makes it anti-linear. On the first, and be careful, mathematicians do it to reverse, unfortunately. And linear on the second argument. Okay. So that takes care of the first two things we wanted to establish in selection rules. The third thing is the expansion theorem. We really also established this. I'll just state in words. The expansion theorem is a generalization of the well-known result that any function, as I mentioned earlier, can be expanded in terms of odd and even functions. As I mentioned earlier, when we go to more complicated symmetry groups, we get more complicated types of expansions. All we need to show, and we've done this before, so it's more just a review, is that any function to which the group operators may be applied can be embedded in an invariant space. So how do we do this? Well, it's very simple. We take the space spanned by the given function and all its images under the group operators. So let's say we have a group G. Let's say it's the set. It's got n elements. A1 we'll define as the identity element of the group. A2 ... an. So what we do is we apply each of these elements. We go A1F, which happens to be equal to EF, which happens to be equal to F. And then we have A2F all the way down to ANF. Now these functions doesn't mean that it's going to be n independent functions, but we get a space that's invariant. So when we take the space alpha 1, and the alphas are just complex numbers, alpha 1F plus alpha 2 A2F plus dot 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 alpha n ANF is invariant under the group operators. Why is this? Well, if we apply a group operator, AI, let's say we have a function g, a general function g is equal to, I'm not going to rewrite it. If we apply like AIG, this is going to be alpha 1 AIF plus alpha 2 AI2F plus dot dot dot. Now AIA2 is just a product of two group elements, so it's going to be some kind of one of the AJs, so we're going to get alpha 2 AJF. And you can see it, eventually we get the same thing. We get alpha, we get n terms, alpha times a group element applied to F. So it's just the fact that the group under the product is closed explains why this is an invariant space. It need not be of dimension m. It could be of dimension 1 for all we know. If F happens to have the symmetry of the group, applying the group operators to it won't change it. But this will be an invariant space, which we can apply our theory of invariant spaces. We can reduce the invariant space of these functions to irreducible invariant spaces, and that gives us when we apply the functions in these irreducible spaces, that gives us the expansion. So this is sort of what we've been doing all along to get the expansion into special symmetry functions. Okay. So the expansion theorem combined with the orthogonality relations, they give us general selection rules. For quantum mechanics, and they're usually of the form F alpha nu, comma D, G alpha prime, nu prime. You could think of D as some kind of electromagnetic dipole operator or some kind of perturbation operator. D is usually a linear operator or a function, but we can justify I won't do it right now, but treating it as a function. So what we do is we expand D in terms of special symmetry functions. Okay, and then the scalar product, then the scalar product above is a bunch of terms of the form we get, like, we would have a whole bunch of these terms, not just one of them, depending upon how this expands in terms of the special symmetry representations. Nu prime, nu double prime represent, or are irreducible reps. So the functions remember, we're treating the linear operator D as a function. And there are total number lambda nu double prime times lambda nu prime of these products themselves span an invariant space called the direct product space, and see addendum A, which covers this, and in the later video I'll cover it more formally. So and this space, so the space transforms as the direct product. It's usually not irreducible representation. And we can usually reduce this space. We'll call it gamma nu prime, direct product nu double prime. This will be equal to AI, the sum over I of gamma I, all applied to, like, the group operators. And gamma I is the ith irreducible rep. So if this reduction does not contain nu, let me write that as, I used to automatically delete that. If it does not contain gamma nu, then this scalar product here will vanish. So that's the main application, the selection rules. And the series above, this series over here, is often referred to as a Cleffs-Gordon series, and the AI as the CG coefficients. And the student should be familiar with these from the addition of angular momentum in quantum mechanics. Now, so with the selection rules, one aspect is the Cleffs-Gordon coefficients. Also, I mentioned earlier things like the Wigner-Eckart theorem. And they come in with getting products like these. And if you noticed, I sort of skimmed over treating a linear operator as a function. So the Wigner-Eckart theorem sort of justifies this, and that's what that refers to, where we can expand operators in the same way that we expand functions in terms of the irreducible representations of the group. So that will be it for the selection rules. We're not going to actually do any calculations. You've done enough of these in quantum mechanics courses, hopefully. And next time I'll come back and I'll sort of give the how group theory interacts with perturbation theory. And it's sort of like handles things like degenerate perturbation theory, sort of makes it more clearer. So thank you for watching. I'll see you in the next video. Bye-bye.